today we'll have the opportunity to go over the first module or the first chapter. It's all about general idea about chemistry. We'll handle the basic chemistry here, as the title of the module says, is essential ideas of chemistry. So we'll go through basic ideas. And as you can see, that chemistry is always, the history of mankind was always the center of the interests of humans. That goes all the way back for the Greek, the Egyptian pharaohs, the old Chinese. So those are, and the alchemists. You might have heard about the alchemists. So this is because most of the chemistry is coming from the nature. And you can imagine yourself and ask yourself, how come people, thousands of years, I will not say millions of years, we don't know, thousands of years, they healed themselves. They had healed themselves from diseases, correct? How? So it turns out to be, they turned themselves out to nature. And most of the trees, the best healer, the best drugs are coming, the best medicine are coming from the trees, and then from the soil itself, correct? And the soil. So those are two components that help mankind survive through all these thousands, maybe millions of years. No hospitals, no medicine, no nothing. So they healed themselves through trial and error, taking some of the trees, some of the soil, and work on those areas. Correct? So this is just to give you some examples here. Alchemists, they did a lot of stuff, and sometimes deadly stuff. Some of them died from mercury poisoning. They extracted mercury, and they tried mercury on themselves. They swallowed, they have taken in their body mercury to see the effect of it. And most of the time they end up dead. So the alchemists, they really trial and error, and they did a lot of really courageous chemistry. It's not normal chemistry because they have to try it themselves on themselves, and they end up damaging themselves and killing themselves. So some of the modern chemists in the 1600s, you see him, Robert Boyle. Robert Boyle has a lot of contribution, not only in, he's a biologist. At the old time, the 1600, 1500 people, they were a chemist, physicist, physicians. They have multi degrees. They can handle a lot of degrees. He's a biologist as well as a chemist. So he had contributed to the gas law, and is honored by his name, called Robert Boyle's gas law. Boyle's gas law will tell you if you increase the volume up, the pressure will go down. If you decrease the volume, the pressure will go up. So indirect proportional relationship between the pressure and the volume of a gas, any gas. And he further defined, even went into the elements, but he did not go in depth in that. So Dalton theory, or Dalton's another chemist, he went through this in depth about the elements and what this element is made of. Correct. Other names of scientists here: Joseph Priestley discovered the oxygen gas, 1700, and he's the founder of the combustion reaction. Combustion reaction is what's the real name of the combustion reaction? Fire, correct? Fire is combustion reaction. Whenever I say combustion reaction is fire, fire is made of burning matter, any matter, organic, non-organic, with pure oxygen. In pure oxygen, the pure oxygen will come and oxidizes the matter, and then you'll end up having complete combustion CO2 and H2O, or incomplete combustion, which is carbon dioxide, CO2, H2O, and a little bit of soot, carbon charcoal. So he's the founder of the combustion reaction, which is the fire, studied it, and he worked on the fermentation. The fermentation is you can make out of rice, out of potato, out of some veggies, some fruits, most of the fruits, grapes. You can make out of them alcohol, ethanol, correct? And you need the fermentation. You need the bacteria from the air will come, will help you to convert the material you have into alcohol. Now, we have to be careful whenever we say this. I had in Germany a roommate here is making his own alcohol. And I was telling him he has to be advised, you cannot do that. Because you not get only ethanol, you get isopropanol and other side products. And if you take it, you can poison yourself and you can kill yourself. So the fermentation reaction works for a couple of weeks and you get ethanol. The majority of the amount is ethanol. However, you might get other side products of alcohol, isopropanol, butanol, which is not healthy. Methanol can cause blindness and death. 15 mL can cause death. So you have to distill it. After you are making your fermentation of potatoes or of rice, you can make all those carbohydrates, you can make out of them ethanol with the help of the bacteria from the air, fermentation bacteria. Then you have to go through distillation to get the fraction of ethanol plus 78 degrees Celsius out of the rest of the other poisonous alcohols. It's not drinkable. The only drinkable is methanol causes blindness and death. Isopropanol can cause a lot of stomach disturbance. You can just keep vomiting for days. And butanol can cause death as well. So the only thing is drinkable is ethanol and has to be distilled in its fraction distillation to get it out of the other fermentation products. Are you following me here? So that's the Joseph Priestley here had the fermentation reaction. And if you go for biology next semester or this semester, I think they do have fermentation, I think. Microbiology or A&P, they do have fermentation experiment. Now, you mentioned just 2 examples. Are there too many scientists contributed to chemistry? The 1500 modern chemists? Yes, there are many. But just 2, I gave you 2 examples from our ebook, but there are too many to count of those, but we counted just very few of them. So chemistry as a central science. Well, it turns out to be, if you put the chemistry as it's in the center, as a core, then you will see all the sciences will be circling around chemistry. Chemistry is contributing to all sciences, no exception. No exception. Chemistry is contributing to biology, contributing to astronomy, physics, environmental sciences, geology, all the other sciences, and even engineering. So chemistry, therefore, is called the central science of all sciences. Chemistry is the central science of all sciences we know. I will even exaggerate a little bit and say even engineering, not only sciences and engineering. So you will see chemistry all over the places, from your clothing to your car to your food, all is chemistry involved in it. So we like it or not. So chemistry is the central science of all sciences, and for my part, and engineering. So and engineering as well. And here's just an example. Here will give you this chemistry is related to geology, to ocean science, to ocean science, to hearing, physics, astronomy, and so on, biology and astronomy, all these sciences, environmental sciences, all those sciences are connected to chemistry. So, and here I said, so forensic science, that's a science by itself, which is really is a mixture of chemistry and biology, correct? Mixture of chemistry and biology. Okay, so the scientific method. What is the scientific method? Well, it turns out to be the scientific method. You'll start with your observations. You observe, correct? Your observations will be based on two items or two components. One is qualitative. You see the stuff as they are. You record your observation as they are, correct? There's nothing there. So, but there are some quantitative observations, which is really based on quantity, correct? Quantity. So you will see like 15 grams, 20 grams, or the volume 20 mils. So there is quantity there. So you make a qualitative and quantitative observations to a phenomena or to anything. You can just look at it. So you start your scientific method by observations, qualitative and quantitative. When you did your observations, then the next step to make, you have to ponder, you have to think about these observations, qualitative or quantitative. You have to think about them. You make a hypothesis. Hypothesis is just a thinking, an idea based on your observation or observations, qualitative or quantitative. Then when you have this idea here, so we started with observations, qualitative, quantitative, then we go further to make an idea about what's going on. This is hypothesis. So, and now after hypothesis, I have to test this hypothesis. I have to go to experiment. I have to go to the lab to test my hypothesis, whether it's correct or not correct. So I do experiment. If the experiment is good and that my observations and my hypothesis, my whatever statement I made over these observations, I make this one here, this experiment here, can be what? Can be elevated to a scientific law. Now, scientific law is not only my thinking or my experiment. I have to have the help of all other scientists all over the globe to do the same conditions I made in the experiment and come up with the same data and the same results. If they come up with something different, then my scientific law is not accepted as scientific law. It is a theory. Still what? A theory. Theory is based on the hypothesis. I made some stuff, but it's not 100% correct. So I have to make modifications of this theory here to elevate it to the level of scientific law. Scientific law does not change per year. Does not change unless it's serious errors or we did something big mistake. So scientific law, whether you are on the moon or you are on planet Mars or you are deep in the ocean, thousands of feet inside the ocean, this law will not change, will give you the same results. That's the scientific law, it does not change. A theory means you are struggling with your experimental setup, your conditions, and you are not getting the observation. You get part of the observation you have, but not all of it, correct? So let's summarize this. What is scientific method? Scientific method, you start with observations, two types, qualitative, quantitative. Qualitative just by observing by your eye. Quantitative, you have to count. There is some quantity inside, correct? And then you couple those two observations together and make a statement out of it. This statement called hypothesis. Then you want to see if this hypothesis, this statement you made based on your observation, is correct or it's not correct. You have to go to the lab, whether you are in physics lab or whatever, in any lab. You have to test this hypothesis or this statement, whether it's true or not true. If it's true and supported by many, many, many scientists throughout the globe, then it is now law, scientific law. Meaning anywhere in the world here, somebody will do the same condition, the same experiment, that scientist will get the same data you got here in your lab. That's scientific law. However, sometimes we are not lucky, we will not get all the observations through the experiment is really approved or get them correct. So you get something, part of the statement's correct, part of it is not correct. In this case, we have to go back to the lab, remodify the conditions, and do something else and work on this hypothesis. And this type of working called the theory. So we are in the stage of theory. So theory is not the highest state. Scientific law is all the way up. The theory is still struggling to prove itself to be scientific law. But always theories can be changing per time. Scientific law, they don't change per time. That's the difference between them. Make sense? Any questions so far? Any questions so far? Okay, so here it is about the it's about the scientific method. Start with observation, qualitative, quantitative. You make your hypothesis statement, and then you have to go to the lab. You have to make an experiment to see if this is really your observation is correct, your statement is correct, and the hypothesis is correct, and is supported by the experiments you did. So then you ask other scientist communities all over the globe and ask them if they will share with you the same, and give them your data and your stuff, your conditions, and then they will do the same conditions everywhere, every labs. And then if they get the same thing, then the scientist community will come up with the statement, this is true all over the globe. This is a scientific law. Now, if we have a problem with this, then we say, okay, we have a problem. So part of the hypothesis, part of the observations are met through the experiments, but the other part is not. So we have to go back to the lab and re-modify the stuff. We are doing the conditions, and we speak about what? About the theory, which is not elevated to the scientific law. Make sense, guys? Any question you have? And here, just an example. You can look at this, just an example here. An examples here. So what is observation? What's hypothesis? What's experiment? And then how you get bottom here, how you get your theory out. Here it is. So you can read an example. I gave you an example here, just in general. So if you look at this, some problems here. If you look at this, it says here, for example, ice always flows on liquid H2O. Is a general statement of a relationship between properties of liquid and solid H2O. So it is a law. So what is this law? It says, if we look at the first one, see if it's not working. Well, I will use the mouse here. Maybe a green one. So if I look at this one here, this is a law. But what this law is based on? Why this iceberg is floating? Why? On the ocean, why? It turns out to be, that's a scientific law. The density of ocean, H2O, is higher than the iceberg. So the iceberg will float. Anytime I have a comparison between the density, the higher density, correct, will sink. The lower density will float. If you have, for example, a mixture of three components: a cork, plastic cork, correct, and tabor, and oil. So, and then you are asked by your instructor, lab instructor, to label them. Who will be at the, which one will be at the top, which one will be at the bottom. So which one will be at the top? The cork, correct? It's the least dense, will be at the top. Then what? The oil, that will be the second, which is higher dense, more denser than the cork, but less dense than H2O. And H2O is heavier, will be at the bottom. Now, if I add sand, a fourth component, the sand will be heavier of all those three, will but think all the way at the bottom. So at all the bottom of the beaker or test tube, you have a sand, H2O layer, oil layer, and the plastic cork layer. So therefore, you can see it's a scientific law. It tells you that the higher the density of the material, the deep it will sink. So that's a scientific law. Now, here the second one, birds were evolved from dinosaurs. Well, it is a possible explanation, but there is no evidence for this because you did not see that. So at least the first one, the eyes, you saw that. You made an experiment and you proved this one true. Birds are evolved from dinosaurs. Well, it might be, it might not be. So this is a theory. You made a theory, but there is no or hypothesis, theoretical hypothesis. So you don't know because you don't have the way to make an experiment to prove it. Correct? The only thing you can make an experiment and prove this one here to be scientific law. How we can approach this one here, this hypothesis, and turn it into scientific law. Theory and the scientific. Well, take the DNA of a dinosaur. I don't know from where you get a dinosaur. And then take the DNA of a bird and then see if there is a match in at least of the DNA. Then you can make your statements, your hypothesis that birds may be evolved from dinosaurs, depending on the DNA. Now the DNA, it has to be percentage. 5% DNA is not a good result. It has to be more than half, 50, 60%. The DNA of a bird is equal to the DNA of a dinosaur. Then it will be accepted as a scientific law. Are you following me here? So you can evolve from hypothesis to theory and then to scientific law by doing the actual experiment. So the actual experiment now, they just take DNA from an old dead dinosaur and then from a bird and then compare what's the match. And it has to be more than 50% in agreement with each other. So hot air is less dense than cold air. This is what you made an this is what hot air is less dense than cold air. True or not true? True or not true? That's true because, and that's what you have this tornadoes, correct? What's the tornado? Tornado is just a turbulence between hot air and cold air, correct? Between hot air and cold air. The hot air touching the earth, very hot, and the one coming out cold, they will come and collide. Those molecules come collide and make a turbulence. So the two airs, one cold, one is hot, they come together and they make this type of turbulence because of the temperature gradient. It's a difference in temperatures, correct? So especially in the summertime. Summertime, the bottom, the floor here, the sun is hitting the ground, it's very hot. So the air near the ground or on the ground is hotter than the air coming from the sky. So when the air from the sky cold come in and they hit the air from the ground, which is very hot, then you get the molecules are just colliding against each other, causing a turbulence. That's what tornado is all about. It's just air, hot air, cold air coming to collide together. So the hot air is you can see it's less dense because molecules are what? Moving. The cold air, the molecules are very slow to move. They are not moving that much. So that's the difference between them. So this is a theory, and you can prove it inside the lab as well. You can make a final experiment and prove it to yourself. So let me get out of the, then. Problems here. Let's look at the example here. When 10 grams of ice were added to 100 ml of H2O of water at 25 degrees, the temperature of water decreased to 15.5 degrees Celsius after the ice is melted. What do you think is this? What do you think? It is observation, is it theory, hypothesis, or scientific law? It is not a scientific law by all means, correct? It's not a scientific law. That's not a theory. So it has to be between hypothesis and observation. Hypothesis, you did not make a statement that, that's really affecting. If I make a statement, I'll say, well, the cold ice, correct? Cold ice, when I put the ice inside the normal at room temperature, this is 25 degrees, this normal room temperature. If I put the ice inside the 100 mL of H2O at room temperature, this 100 mL will be cooled down, correct? Be cooled down. So will be cooled down after the ice melted. So this is an observation. It is qualitative or quantitative? It is quantitative. Why? Because I'm dealing with numbers. I'm dealing with 3 numbers. 100 grams. I'm dealing with 100 grams here. I'm dealing with 100 mLs. I'm dealing with 25 centigrade Celsius. I'm dealing with 15.5 centigrade Celsius. So this is quantitative observation. So let's go for the second one. The ingredients of ivory soap were analyzed to see whether it really is 99.44 percentage pure as advertised. So by doing this, what will be? What will be this one? This is not a theory. This is not a scientific law, correct? This is not observation. You took the ivory soap and went to the lab. So you are doing an actual experiment, correct? So, and then you did not make a statement yet, because if it's really came out as claimed, 99.4% pure, then you'll make a statement, correct? Make a statement which is hypothesis. So this is an experiment. So let me just okay, so the math skills required for the course. Well, I'm not going through the math. Please come and see me in person if you have problems in math. I have a master's degree from Germany, chemical engineering. So I'm a chemical engineer. So I love math a lot. So come and see me if you have a problem. So I'm not using my time to go this. This is about high school level of math. It's not really difficult. And it's very, very simple. We will not go through this introduction to chemistry. We're not going for higher chemistry. That's introduction, basic general chemistry. So we'll not go that in depth in math. Very simple math. So, but if you have still problems, come and see me. I will go through this. So I'm skipping the math skills here from in the lecture. I'm not lecturing, but I will be more than happy to help anyone with this math. If you have any problem with math, come and see me in person, because that's I think it's just time consuming to go through all this one here. I mean, we'd rather spend some time on the material, but we can review the math in my office or in the Webex office hours. So Exponent, well, the same thing. I'm not going through this, but you have to know that exponent and the scientific notation. Scientific notation is based on power of 10. So you can go scientific notation, or you can go decimal way of writing number. So the number can be written in two ways: scientific notation with the exponent of 10, or a decimal, which is decimal way of writing. So they have two in the decimal, and then when you switch them back and forth, you have to watch. If you go from decimal to scientific notation, you go to the left, then your exponent will be positive. If you go to the right, your exponent will be negative. Now, going to the left, you are shrinking the value. If I want my goal to shrink the value, make it smaller, then I have to go to the left. And the sign on the exponent will be positive. If I want to go to expand the value of the number, expand it, add too many zeros to it, then I have to go to the right, and the exponent will be negative. So you might have forgotten this from the high school time. Come and see me. I will show you with a lot of examples. Come and see me. But again, this is just math. And if you have any problems, come and see me. Anyone has problems with the exponents and simple math? Those are just very simple math. It's not really difficult math. But I will be more than happy to spend. See here, you can see all this here, examples, you know, how to open the exponent. So 10 power 3, and in parentheses, power 4, that's 10 power 12. You multiply those exponents. And if you, by division, you subtract them, correct? Multiplication, you add exponent, and division, you subtract. Okay, so here it is. This is the same thing with the log. Come and see me if you have any problem with those here. Okay, so let's here it is very important, this section 2 of the module or chapter. What is matter? Well, it turns out matter is anything that has a mass and occupies, and it does occupy. Anything does have a mass and does occupy space, correct? Now, what is antimatter? Halloween is coming, correct? What our ghosts are made of? Come on, guys, don't let me down. Halloween is coming October 31st. We said we have matter, correct? And the condition to have a matter, you have two conditions. It has to have a mass and occupies what? Space. Now, Halloween is coming. We have a lot of ghosts will be around, correct? The ghost can go through the wall, correct? It's not bouncing back, correct? From the wall. It can go through the wall. So what does it mean? So the antimatter is just quite the opposite two conditions. Antimatter does not have a mass and does not occupy space. Can be everywhere. Correct? That's what they call ghost. Ghost. They call it ghost, but ghost means antimatter. So it does not have a mass. If it has a mass, it has to bounce back from the wall. Yes. Well, dark matter and the antimatter. Yeah, but the mass is so tiny. That's electrons. We'll come back to that. Electrons are antimatter. They do have mass, but we neglect this mass, almost massless. But they do have mass. But the ghost, if it has a mass, it has to what? Bounce back to you. Correct? Now, electron, if I have a proton and neutron and electron will go through the wall. But the protons and the neutrons will bounce back because they have really mass, heavier than the electrons. So therefore, every time we see dealing with electrons, we say electrons almost massless. Imagine 10 to minus 24. and you weigh 10 to minus 24 grams, that's very, very tiny, correct? So anyway, remember the extra credit for the Halloween coming. So that's, we'll have some chemistry related to, we'll make some ghosts out of some smoky stuff coming up, but that's not antimatter. So therefore, you see electrons can behave, they have dual, they can behave as a wave or can behave as particle, correct? Light, the same thing. If you have the sun will go through the glass. It's not bouncing back. So it can go through the glass, correct? That's what antimatter. But the light, if you put a mirror with the silver surface, the light will bounce back, cannot go through. So the light has dual character. Electrons has dual character. It behaves as it has a mass, and sometimes it does not have a mass. But the photons of the light the same way. They have a dual character. But their mass is almost massless. We don't really consider their masses. Anyway, so what is the difference between mass and weight? Well, you see how big the whole thing here? Too big, yeah? I cannot take it. But if I go on the moon or somewhere else, even further than the moon, where the gravity is almost zero, can I take this one in my finger? Yeah, with the fingertip, the whole thing. On the Earth, I can't take it. See, we need 5, 6 people to take the whole table. Are you following me here? So we are speaking about not the mass, we are speaking about the weight. Mass does not really depend on the gravity, correct? Weight, however, it does depend on the gravity. In a G0, where there's no gravity, G means gravity, G0 zone, there's no gravity. So everything is flying, correct? Everything will be flying because there's nothing attracting to the core of that planet or meteoroid or star. Nothing pulling, correct? So therefore, the moon, everything in the moon will be less by 1/6. So anything that's weigh on the Earth is 100 grams. So 1/6 of this 100 grams will be weighing less on the moon because the gravity of the moon is smaller than the Earth by 1/6. Are you following me here? So therefore, there is a difference between weight and mass. Mass, if you have your mass will be the same, whether you are on the moon or in the other stars or other planets, other meteoroids, it does not change. However, weight does change because of the power of the gravity pulling that object to the core or the center of that star or meteoroid or planet, correct? So that's the difference between them. So state of matters, we have, according to the whatever we have 3 states. We have solids and liquids and gases. However, we have another one, 4th state. Somebody will tell me what the 4th state is? Plasma, correct. Plasma is the 4th state of matter. We don't consider it that much, but plasma is the 4th one. What is plasma? Right here, we have the plasma. A plasma is a gas that is experiencing a lot of stress. You put high voltage on this gas, which is colorless, that's argon, by the way, that's argon. If you have a neon, it will be very nice purple. So it depends on the color of the gases. You will see the color. The color will depend on the gas itself. So argon has no color. So I'll give you this high condition or extreme condition on the gas will lead the gas to lose some of its valence electrons. When this gas is losing its valence electron, we'll come back and look at that later on. Losing some of its valence electrons, those at the end, the outermost shell, all the way far away from the core or the nucleus, those are lost. When this lost, it start what? Charge. So plasma is a charged gas. Is what? It's not a normal gas. It's now charged gas because it had lost some of its electrons by exposing to extreme conditions. So that's the fourth one. It's not there, or you'll not be asked, but at least you will know that there are four. There are four main ones. There are some, if you look at the literature, there's some other state of matter, but those are inside the nucleus. We are not dealing with them. But this is just, we see them in nature. We have four types of matter: solids, liquid, gases, and plasma. Okay, so next is about property versus intensive property of a matter. Well, extensive means this property has to depend on the amount of the matter itself, always on the amount. Right? So if I have different amounts, I will have different property, and therefore the property is changing. Therefore, I say this is extensive. Intensive, on the other hand, does not depend on the amount. I'll give you an example. Then you'll make in the lab, I think in 2 weeks or so, after we come back from Labor Day, after September 5th, you will do the density. Well, the density of 1 drop of H2O is the density of 2 million gallons of H2O, the same density. Does it change? No. Are you following me here? It does not change. Whether you are measuring the density of 1 drop of H2O or you measure the density of 20 million gallons of H2O, the density has to come the same. No change. That's an intensive, IN, intensive. The extensive here will depend on the amount. If you have a matter and it has 10 grams, take the same amount of the same matter, and then add, instead of 10 grams, take 50 grams. Then you'll see the matter will have changes. So that's extensive. Mass and volume are extensive. Now, some of the intensive does not depend on the amount. Physical properties such as melting point. Melting point does not change, correct? Boiling point, sublimation point, deposition point, all those points or temperatures, they don't change of the matter themselves. So they are intensive, IN, correct? Those are IN, correct? So those are IN. So how about the color? The color of a matter, color of iron, of silver, of mercury. What is this? Intensive or extensive? That's IN, intensive. The color is intensive. Whether you take 1 gram of mercury or you take 10 million gallons of mercury, the color of mercury will be the same. Will be gray, shining gray, the same thing. Whether you take 1 drop of it, mercury, or you take 10 million gallons of mercury, the color will be the same. It's not change, correct? There's no change in the properties. And here, just to give you an example here, if you look, you have a powdery or crystals, sulfur, yellow. That's on your right here. It is. This is powder or crystals, right? Not crystals, but powdery, and just very tiny powder. And this one here is hot rock crystals. See? But the color is intensive. Does it change? No. The color is the same. There's no change. Still yellow, bright yellow in both sides. So the melting point of crystal sulfur and the powdery sulfur is the same. Nothing changed. The boiling point of both the same. So those are intensive. But then if you have the mass or the volume, then this property will change. Even their reaction and all the stuff here, they will change according to their masses, correct? Or their volumes they are involved in. Okay. Now we have to look. We looked at the state of matter. We said solid, liquid, gases, and plasma. And now we have to look at the classification of matter. And we start from the matter itself. We start from an element, correct? An element, that's the start of the matter itself. This element is made of atoms. These atoms are made of electrons, protons, and neutrons. Right? So it's really what you look at the picture is an element that you start with. However, this element is made of atoms. The atoms are made of electrons, protons, neutrons. So you go all the way back to the electron, proton, neutrons. Those are the origin of the matter itself. Correct? Each one of us has those electrons in our bodies, in our food, in our everything. So each matter has to have electron, proton, and neutrons, those atoms, even the soil, the trees, everything, air, in our bodies, everywhere. So that they cut those atoms and make elements, correct? Each combination of those atoms will make specific element. When those elements are combining themselves, they make pure substance or pure compounds, correct? Now, if you mix those pure substances together, then you get mixtures. Those mixtures, you can mix them in two ways: homogeneous mixture or heterogeneous mixture. Homogeneous mixture means those substances are coming in and mixing themselves with fixed layer, and they are really uniform throughout the layers, the mixture layers. So you not see two layers together, you see one single layer. That's homogeneous. Heterogeneous, they don't mix very well. So you'll see two layers of them. So their distribution among themselves is not uniform, is not by all means uniform. Everybody's following here? So let's go back and look. We start from the atoms made of electrons, protons, and neutrons. You make an element. This element is very unique. The combination of atoms will make a unique element. Those elements here will combine themselves to make what? To make a pure substance or a pure compound. Those pure compounds can mix together through two things, either homogeneous or heterogeneous. Homogeneous, they make one layer. They are really uniform throughout the mixing. But if they are not making this homogeneous one single layer, the distribution will be not uniform. An example: if I take salt and H2O, mix them together, the crystal salt is gone, or sugar and H2O, correct? Mix them together, the sugar or the salt crystals are gone or dissolved, correct? I have one layer, looks, no crystals anymore. But if I have oil and H2O, you'll see the oil is less dense, will float, and the H2O at the bottom. So I can see what? Two layers. So, and that's the difference between the homogeneous versus heterogeneous. One more thing, maybe not in the PowerPoint, not even in the ebook, but I would like to add it. The good thing about heterogeneous mixture or homogeneous mixture, they can physically, not chemically, they can physically separate it. I have ethanol and rubbing alcohol. Rubbing alcohol is antiseptic, is isopropanol. It's used if you have a cut, you put on your cut and it will kill the bacteria. So it's very good for killing, antiseptic for killing the bacteria. So if you have a mixture of them, guess what? You'll not see where is isopropanol and where is ethanol. You'll not see them. Very nice homogeneous mixture. But you can separate them physically by distillation. You can distill. One will go further, the other will go later on. Correct? So you can separate them by physical means, not by chemical means. If you start doing any chemical means, you will destroy the structure of both. So, and here is the picture of the matter, that's the elements made of atoms. Those green stuff, those atoms. Those elements come combine themselves. See the purple atoms, and those come and then make elements come and combine themselves to make a compound. This compound can be mixed together in this way or heterogeneous way. And this is just the flow chart. Will show you how you can have started from the matter, which start of electron, protons, and neutrons, and then you go all the way to make an element. This element is very unique. Some atoms will make those elements. Elements will make compounds. Compounds will make mixtures. You can separate those homogeneous or heterogeneous mixture by distillation, filtration, extraction, all other techniques. Any other question? I'll stop here, and I'll stop recording here. And I hope that we got everything. We will see. Okay, I will meet for you then